This is Lab 2, which is motion of a falling object. So our introduction, what is the problem? Today we're going to be studying the differences in an experimental model of an object falling, along with a computational model that only has gravity as an acting force, and another computational model where gravity and drag are both accounted for as forces. Why are we interested in this answer? It's going to help us see if the drag force significantly affects a falling object. So a quick summary, accounting for the drag force does make a slight difference in objects that fall slower than a rock because the drag force does slow the object's path. However, the difference is really not large. So our fundamental principles. First, we have Newton's second law, which is just initial velocity is equal to final velocity plus the net force divided by the mass times the change in time. So an initial velocity of 0 with a falling object then turns into a much larger velocity at the end. This means the net force cannot be 0 because the velocity is changing. A force diagram is going to show how the net force includes gravity, which is negative mg pointing downwards, and also drag force, which is our air resistance pointing upwards, as you can see in this model right here. So the video I use with Tracker is just a ball crumpled up paper falling. And so I put this into Tracker, and it exported this graph right here, our position versus time graph. And here is that data that goes along with it as well. You can see the x moves slightly, but we're really focused on the y. And so the first computational model, here is our code. The only things that were changed are down here, where the negative ball point m times g times j hat, that's going to be the weight, which is just negative mg. That is our net force. And over here, we did the velocity Newton's second law formula, and down here, we did the position update formula instead. And now here's a photo of what it looks like when you run the code. Here is a position versus time graph that the code exports. And here is our experimental graph along with our computational graph. Now you can see that there are some discrepancies, especially where it crosses right here, and slight discrepancies up here as well, but they are fairly close. And these discrepancies are largely due to the negative mg force being larger going downward in the computational model. Now we're going to edit it to include the force of drag. So up here we have the drag force is negative b times the velocity of the ball. We set b to 0.0017 using trial and error to kind of see what the constant should be. And we have the net force is w plus fd. And